You guys seen these kinds of things before? Yeah. I got these. I took these from my son. They don't work anymore. But these are, yeah, they have LEDs on the inside. That's why they light up. Right? You haven't seen these? I don't know, actually, because it's broken. But there are LEDs in here. They're supposed to light up at night, so you can. I'm going to use them for a demo. Okay. We're doing diodes today. I mean, light emitting diodes, for real. Okay, why don't we get started? Just an announcement. You know, every 2 weeks you'll have a quiz. So the next Tuesday there'll be the third quiz. It was announced on the website this weekend. So it will cover pretty much just PN junctions. So everything up until last Thursday, which you have a homework assignment on this week. Okay, so it's closed book. You can have yet one more page of notes, so you can add, so you have a total of 3. And again, you should not need a calculator or any other electronic device to assist you. Okay, and there will be a review session tomorrow. It's just to review things that people missed on the first 2 quizzes. Tomorrow at 5 o'clock in, I think, the classroom right next door. Okay, so just 1 hour. It'll be short. Just want to review things that a lot of people missed. Okay, so today we're going to finish the topic of PN junction diodes. So last time we talked about transient response, why it takes, there's always some delay when the circuit wants to switch a diode off or from forward bias mode to reverse mode, why it takes some time for the diode to fully respond. And that's because it takes time to remove the excess minority carrier charges stored in the quasi-neutral regions. So today we'll just look at the opposite case, where we start with a diode that's off, and we'd like to see how long it takes to turn on. In other words, how long does it take to build up the excess minority carrier charge concentrations in the quasi-neutral regions? Then I'll just summarize all of the important concepts that you should know about diodes as we go forward. Because later when we look at the optoelectronic diodes and when we look at the bipolar junction transistor, you'll need to know these basic concepts for the PN junction diode. And then finally, we just end the lecture today looking at various applications, common applications of PN junction diodes. Okay, so let's finish up the discussion on transient response of PN junction diodes. So let's say now we have a PN junction diode that's much more heavily doped on the P side than the N side. So when it's turned on, most of the charge, excess minority charge, is stored on the lightly doped N side. Okay, so now we're only going to look at the excess hole concentration on the quasi-neutral, in the quasi-neutral N region. Right, so this is the N side. So with time, so what happens is that over time, okay, so when you first when the circuit in which the diode is connected first starts to flow forward current and applying a positive bias voltage and flowing current into the diode, that's going to cause charge to build up. So you're going to see something like this charge building up with time. So this is basically what it'll look like with increasing time. So basically what I'm saying is that the circuit will force some forward current to flow through the diode beginning at time t equals 0. Okay, so this forward current, I sub f, is just dictated by the circuit in which you are operating the diode. So what will happen is that initially you'll flow holes into the quasi-neutral region. Some of them will die out before they reach the contact and so on. But basically over time, the concentration of holes will grow. And the key thing to note here is that the slope at the edge of the depletion region is constant. So at any moment in time, a time t greater than 0, the slope at x equals xn, right at the edge of the depletion region, is the same. Okay, so can somebody explain why that's the case? fact that the circuit is forcing the diode current to be constant with time. Right, so the diffusion current due to holes, which is the dominant component of current in this one-sided junction, the slope, whatever slope there is at the edge of the depletion region, has to be the same for all times, because that slope determines the whole diffusion current at the edge of the depletion region. Okay, which determines the current flowing across the junction. So that's the reason. So eventually, then, this charge density profile, this is proportional to the total charge, minority carrier charge stored in the n side due to holes, eventually will reach the steady state, profile that is dictated by the forward current. Okay, so eventually, so as we know, for time t much greater than 0, we know that the diode current is going to be equal to I naught approximately e to the q VA over kt. Let's say it's strongly forward biased, so we can ignore the -1. So then we know eventually V of A has to reach kt over q times the natural log of IF over I naught. I mean, eventually, right? It's just going to take a little bit of time for the voltage across the real voltage across the junction, the PN junction, to reach that level. And it takes time because Q sub P has to build up. So remember, from the charge control model, the current is equal to Q sub P over tau sub P in steady state. Okay, so this is this is also for a one-sided junction, right? We had a minus Qn over tau n here, but we're assuming that this is negligible because it's a one-sided PN junction. So so once the charge in the quasi-neutral region charges up, then you can reach the steady state value of the applied bias needed to support that current. Okay? The question is, why is the current a step function? Okay, so the current is a step function because it's dictated by the circuit. So the circuit can actually force current to flow through a diode. And that current serves to charge up the quasi-neutral regions. But the voltage that appears across the junction of the diode will slowly build up until it reaches that steady state value. That's dictated by the forward current. Okay, so it's that way only because the circuit forces it to be that way. Okay. That's right. So the slope at the edge of the depletion region is forced. So this little I is going to be IF. Right. That slope is dictated by the circuit. But in the end, when it reaches the steady state, that slope naturally will match the value needed to give IF. Right. When you reach the final state, it will have the correct slope by definition. Okay. Yes, Andrew.
Wait, so if you have like then one-sided diode or
Oh, a narrow base diode? Are you asking about narrow base?
you need to have a changing, right?
Oh, that's a good question. Okay, so the question is, if it's a narrow base diode, because it always goes to 0 at the contact, then the slope will be changing. Well, I just said the slope is dictated by the circuit, so it can't. Okay, so let's see. That's a good question. Let's think. So for a narrow base diode, so let's say this is delta P n of x for a narrow base. So let's say a narrow n side. Basically, what will happen is the slope will still be the same until, basically it'll reach steady state when you reach the width of the quasi-neutral region. Right? Right. So this will be what happens with increasing time. It still takes time to store this excess charge in the narrow base region, I mean narrow quasi-neutral region. Okay, so it might be a little clearer once we finish this slide. So this is just a derivation of, just to allow us to approximate. Oh, I forgot to go over the last slide from last one. Okay, we'll come back. So this is just, on this slide we derive an approximate solution for the voltage across the junction as a function of time. Okay, and that we do that by starting with the charge control model and the minority carrier diffusion equation, or continuity equation from last time. Okay, so remember last time I showed the water flow or liquid analogy. This is exactly the same equation, okay, except now we have slightly different conditions for t greater than 0. So if we take this continuity equation and we move, the dt to the right, and that's right, and then move like tau sub p to the left, and multiply both sides by tau sub p, we can integrate from time t equals 0 to t. We can actually get this equation here, that the charge as a function of time is just going to build up exponentially in the diode. Okay, so it's going to look something like, it's going to look something exactly, not really. Okay, all right. So at time t equals 0, the charge is 0, right? Because this term is 0 and this whole quantity in the parentheses is 0. So it goes from 0 to if tau p sort of exponentially. So it was basically. And we know that because in steady state from the charge control model, if equals qp over tau p. Okay, so that's pretty straightforward. Okay, but what we're interested in is actually the voltage. How long does it take for that applied voltage across the junction to reach its final value? Well, we can actually rewrite that equation. Let's see. Okay, so basically what this is assuming when I say that storage charge occurs quasi-statically is that, what does that mean? That I, as I wrote over here, is qp over tau p at all times. And so that's I naught e to the q va over kt minus 1. Okay, so we're just assuming as things are changing, qp is changing, va is changing, we assume still that this ideal diode equation relationship still holds while the diode is charging up. So if we assume that, then we can just rewrite that equation to find the applied bias across the junction as a function of time. And so then, again, you can just see it's just a characteristic time constant, tau sub p. And qualitatively, if the forward current is larger, then it will take, the final value of VA will be larger. Okay, but qualitatively, in terms of time taken to reach the final value, it's just really the minority carrier recombination lifetime that determines the amount of time needed to reach the final value. Okay? Okay, qualitatively, all you have to know is that the longer the lifetime, the longer it takes to reach steady state. Okay? Qualitatively, why does that make sense? Why does it take longer to reach the steady state value of charge stored or the voltage applied if the recombination lifetime is longer? It's very simple. It's nothing tricky, I don't think. Yes? Yeah, but see, so this is why it's a little, so maybe it's a little tricky. If the recombination lifetime is longer, then it won't die out as quickly. So when you flow these minority carriers into the quasi-neutral region, they won't die out quickly. So it should be able to build up faster. So if the recombination lifetime is long, and as you add holes to the end side, they're not dying out. So you're able to build up the charge faster it takes longer. It's very simple. It's simply because to reach the steady state, you have more charge needed. Right? If you just look at IF equals QP over tau P, QP is just larger if tau P is larger. So you just have to build up more charge to reach the steady state. That's all. Okay. Okay, so sorry I forgot to go over the very last slide of last lecture. Just qualitatively again, I don't think I drew the answers here. So what do you think? Did any of you even think about these over the weekend? No, just kidding. Okay. So turn off. Let's say we start with a diode in the on state, flowing some forward current, and then we suddenly, at time t equals 0, force the diode to suddenly turn off and go actually into reverse bias. What will happen in each of these three scenarios? So this is a typical question, type of question we could ask on a quiz. Okay, so if we increase IF, that means before we turn off the diode, it's flowing more current. Okay, so when we turn off the diode, this minus IR, okay, this, let's assume that doesn't change. The circuit is still forcing some negative reverse bias current to flow initially. How is this curve going to change compared to the black curve? Yes? Very good. So the storage delay time will increase because it takes longer because if IF is larger, then the amount of charge, QF stored in the on state is larger. So it just takes longer to flow out the charge. Very good. Okay. Now what if we don't change the forward current, but we increase the reverse current? So you're getting rid of the stored charge faster, so you'll have a shorter storage delay time. And finally, if you decrease the recombination lifetime, so we're not changing these values, IF and minus IR, what do you think will happen to the time it takes to turn off the diode? Increase tau P. So that means they die out faster. Yeah, so it's to the left. That's right. Very good. And in principle, you should be able to do this kind of exercise for turn on as well. Okay, great. So this, I think for transient response, you just need to know qualitatively what's going on here. Okay, but interestingly, if tau to P is large, so this is the comment that was maybe alluded to earlier, if the recombination lifetime is large, so in other words, if recombination is negligible, what do you think? What do you think is going to be the amount of time needed to actually turn on a diode? In other words, as you inject minority carriers into the quasi-neutral region, it's not going to die out. Okay, well, the answer is here. So basically, when the diode is turned on, it has to have some excess minority charge stored in the quasi-neutral region. And you had to inject some, let's just draw here. In N region, you have a depletion region on the left, have a depletion region on the right, like this. And your circuit is forcing some forward current to flow here. Okay. This is the excess, let's just review, excess minority carrier charge. This is stored in the quasi-neutral region, regions. And if you had significant charge on the P side, you would add that here as well. Okay, and then this is charge stored at the edges of the depletion region. Well, yeah, it's equal magnitude on both sides. Okay, so basically, if you change the bias, if you change the bias across the diode, you need to change the amount of charge stored in the quasi-neutral regions, and you need to change the amount of charge stored at the edges of the depletion region. So let's draw a different color. So you have holes entering in from the metal semiconductor contact on the P side, right? Majority carriers flowing in. So some of those holes are going to be used to cover up the ionized acceptors on the P side to shrink the width of the depletion region. And some of them will diffuse across the junction and charge up the quasi-neutral, well, not charge up, but build up excess hole profile in the quasi-neutral N side. And same thing for electrons coming in from the N side, from the metal contact. Some of them will be used to cover up some of the ionized donors on the N side to shrink the width of the depletion region, and others will be flowing to the quasi-neutral P side to build up the steady state level of excess minority electrons on the P side. Okay, so basically, the amount of time it takes to inject all this charge into the diode is dictated by the rate at which you're flowing charge into the diode. Right? IF is essentially charge per unit time. So the rate at which you're flowing in charge into the diode, that's going to dictate how fast it takes, the fastest you can actually reach the steady state with your diode. Okay? Does that make sense? Okay. I think that's it for diodes in terms of all the fundamental concepts. So let's review for the last couple of weeks. Forward bias. So remember, under forward bias, if you look at an energy band diagram, you should be able to tell if a p-n junction is under forward bias because the total amount of band bending should be small compared to the band bending you get in equilibrium. Okay, so generally that means the total amount of band bending is significantly smaller than the energy band gap. Okay, so when you lower the potential barrier for carrier diffusion across a junction, you get, because of the concentration gradient, the majority carriers on each side are going to diffuse across, and they become minority carriers on the other side. So we call this minority carrier injection. And those minority carriers cross the junction, they become, okay, the carriers cross the junction, become minority carriers, and die out in the quasi-neutral regions because they see all these majority carriers now of the opposite type. And they can recombine over as they flow in the quasi-neutral region. Okay, so the current flowing across the junction is comprised of both electron and hole components. And usually if one side is much more heavily doped than the other, in other words, if it's a one-sided junction, then one of these current components will be dominant. So if you look at the diode saturation current, it's I naught. So that's the pre-exponential factor. So it's going to be Q times A, because the current is always proportional to the cross-sectional area of the junction. Okay, so let's review again. Due to holes, let's look at holes first. Holes diffusing, so it's d sub p. On the N side, they'll die out roughly within a distance of L sub p. So the concentration gradient is inversely proportional to L sub p. But their concentration, which determines the current, is proportional to Ni squared over Nd. Very good. And you have to multiply by Q, e to the QVA. Okay, I'm not going to, let's just say I equals this over KT. But it's proportional to the excess carrier concentration, so you have to multiply by -1. Okay, so that first term is for holes diffusing into the quasi-neutral N side. And for electrons diffusing into the quasi-neutral P side, they have a diffusivity or diffusion constant of d sub n. The concentration gradient is proportional, inversely proportional to L sub n. They're proportional to Ni squared over Na. And concentration is enhanced again by the same exponential factor at the edge of the depletion region. Okay? All right, and then remember that if we have short quasi-neutral regions, then we have to replace these one or both of these terms with the width of the quasi-neutral region rather than the diffusion length. Okay? So just remember, so this is electron diffusion side. That's the term, and then this term is electron diffusion on n side. Okay, so if Na or Nd, one of these is much larger than the other, usually only one of these terms is going to be significant compared to the other. Okay. Okay, in a long base diode, so this is talking about optoelectronic diodes that we're going to cover today. If you have a long base diode, you're going to have recombination of of the minority carriers in the quasi-neutral regions, and light, basically photons, is emitted. That's not grammatically correct, but light is emitted if the semiconductor has a direct band gap. In other words, you can have an electron and a hole recombine without a trap, so an electron can lose enough energy to generate a photon in the visible wave spectrum. So I guess, okay, technically this should be visible light. Okay, because the electron, silicon indirect semiconductor could emit light if you go from the trap to the valence band. It's just not, you're not going to see it. The wavelength's too long. Okay. So basically, direct band gap semiconductors are generally 3-5 semiconductors. So the light emitting diodes are all made of various alloys or combinations of 3-5 semiconductor materials. Okay, so relevant to a bipolar junction transistor, which we will cover towards the end of this course, the ideal diode equation also naturally stipulates the ratio of the hole diffusion current across the junction and the electron diffusion current across the junction. Okay, so if you take these two components of carrier diffusion and just take the ratio, you get this fraction. Okay, so this is important later when we come back and talk about PN junction, bipolar junction transistors. Now the reason why we keep track of Ni squared on each side of the PN junction is because in the most advanced bipolar junction transistors today, the material in the P side is actually silicon germanium. So it has a slightly smaller band gap. So the Ni squared is larger. So if you have slightly different band gap on the P side versus the N side, you take that into account in the Ni squared term. Okay? So that's why explicitly we haven't canceled it out here. Okay? All right, so just keep in mind that in the future, if you know you're forcing holes to flow across a PN junction, then you know already automatically the rate at which electrons are flowing across the junction, because it has to satisfy this relationship, this ratio. Yes, Paroma. Yeah, so the question is, if you have different band gap materials on the P and N side, yeah, for calculating I naught, yes, then you cannot pull it out. That's right. Okay, so that's under forward bias. Under reverse bias, which is relevant for solar cells and, well, not solar cells, light detectors, photodetectors, this is the relevant phenomenon that we care about. So minority carriers are what we call collected into the quasi-neutral regions of the diode. So let me go back to red. Oh, this is that's horrible. Okay, let me draw that again. I wanted you to sketch the energy band gap, the band gap diagram, the energy band diagram for a reverse bias p-n junction diode. What you should do is maybe first draw like the same band gap on the p and n sides, and then what would you like? What do you like better, p plus n junction or n plus p junction? P plus n. Okay, then it should look something like. Most of the voltage drop is on the n side. Okay, energy band bending is on the n side. Oops, so I should have drawn, this should line up like this. Okay, so here's the p side, here's the n side. And how can you tell that this is a reverse bias diode? Band bending is what? Big, yeah, okay. Big compared to what? To band gap, right? So remember, the built-in potential, VBI, is always going to be less than the band gap energy, okay? And if the total band bending here is clearly greater than the band gap energy, then you know that Q times VBI minus VA is greater than band gap energy, so it has to be greater than. Did I do that wrong? Oh yeah, has to be greater than VBI, QVBI. Right, and so in other words, VA has to be negative. But don't, yeah, it's not good to remember VA is negative. What matters is that the potential barrier to diffusion is large, so that's like reverse bias, because it's less easy for carriers to diffuse across the junction, so less current will flow, okay? Okay, so if an electron hole pair is generated, like let's say by shining light on the semiconductor, the electrons will go to the right because of the built-in electric field that exists in the depletion region, and holes will move to the left. Electrons are going to move out, holes will move out to the left. So the current is going to be less than 0, right? The current flowing through the diode will be less than 0. Okay, so the more light you shine on this p-n junction, the more negative current is going to conduct across the junction. Okay, and so, okay, so typically, what is a typical depletion width? Let me change the colors here. So far, based on the homeworks that homeworks that you've done, what is the typical depletion width? Is it greater than or less than a micron? Less than a micron, good. And typically, what are Ln and Lp? Are they greater than or less than a micron? Greater, typically. So, where do you think, if light is shining uniformly all over this junction, H nu, okay, and light energy, the photon energy, is enough to generate electron hole pair. Where do you think actually most of that current is generated? That's right. It's in the quasi-neutral regions, because quasi-neutral regions are much larger, longer. So remember, any electron hole pair, any minority carriers generated within one diffusion length of the depletion region will diffuse to the depletion region and get swept across and collected. Okay, so that's right. Right. So it turns out that this can be dominant depending on your p-n junction diode structure. Okay. So I'll say it's usually the dominant contributor to negative diode current when you shine light on it. Okay. So we're going to talk about we're going to talk about a special case. So the exception, well, this is usually dominant except in a PIN diode. So we'll talk about that in a few slides. And you have that for your homework for next week. Okay, so those are the basic concepts that you should remember for forward bias and reverse bias. So you should be able to recognize an energy band diagram in forward bias or in reverse bias and explain how current flows and what the dominant current flow mechanism is. So under forward bias, the dominant current is diffusion. Under reverse bias, the dominant current is actually across the junction is drift, even though you have diffusion into the depletion region. But once it goes across the junction, it's drift in reverse bias. Okay, so let's look at a few applications for PN junctions. First of all, for the homework that I think you had turned in last week, you had to look at the dependence of the diode current on temperature. So it turns out the PN junction current is very sensitive. It's a sensitive function of temperature. So around room temperature, let's say plus or minus 10 or 15 or 20 degrees, you can actually get orders of magnitude difference in diode current. So you can actually build a simple circuit to detect changes in current, changes in temperature based on changes in current. But qualitatively, which if I didn't show this middle thing in the legend in the middle, okay, in general, as you increase temperature, does the curve shift to the right or to the left? Not looking at the legend. You remember from your homework? Well, let's say qualitatively. Okay. So maybe I should draw under forward bias. You have, well, that's not really forward bias. That's kind of like under forward bias, right? Because the band bending is clearly less than that under equilibrium. Okay, so what's the dominant mechanism of current flow? Is diffusion of carriers that have enough potential energy, enough kinetic energy, so they have kinetic energy more than this so that they can diffuse across the junction to the other side. Okay, so what do we know with the number of carriers with high kinetic energy? How does that change as you increase the temperature? You get more, right? You get more carriers with a high average kinetic energy, or the average kinetic energy of electrons and holes on each side of the junction increases. So the probability should exponentially increase that carriers can flow across the junction. So for the same voltage, you should get more current. So higher temperature, let's say at this voltage, maybe at room temperature you don't get much current, but if you heat it up, you can get significant current. Okay, so clearly then, hopefully, obvious this is increasing going to the left. Okay. All right, that's a simple way to use a PN junction. Another way for, let's say for radio, I know you probably don't use radio too much anymore, right? But what we can do is we can operate a diode in reverse bias. Okay, so this is a reverse biased diode. So ideally, very little current flows. But we can pass an AC signal, a time-varying signal, across the diode, okay? And let's say there's going to be some bias, like minus VA, okay? So minus VA determines, so minus VA equals the reverse bias VR in this slide. So under reverse bias, what changes as you increase or decrease the reverse bias voltage? Right, the depletion region width changes. Ideally, the depletion current doesn't change much. I mean, the reverse bias current doesn't change much. But the width of the depletion region changes. So the junction capacitance changes. So this is right here, the junction capacitance. Okay, so the junction capacitance, depending on the doping profile, abrupt is what we've been studying, a step function, step doping profile. That's kind of what we've been studying. But we can actually we can tailor during the fabrication process the doping profile so it's linear or has all kinds of, it can have all kinds of possibilities, different profiles, doping profiles versus distance. So then we can actually we can adjust the dependence of the junction capacitance on the applied reverse bias. But in any case, you can, so you can tune the small signal capacitance, okay? and hence the frequency of an oscillator, or oscillation frequency of a circuit. So if you might have seen this in EE40 or the equivalent. So the fundamental frequency of oscillation is like, there'll be some inductor in the circuit and then some capacitor. Basically, you can, like when you, in the old days when you tune the station on the radio, you tune the frequency, the transmission frequency. So a reverse bias diode can be used as an adjustable capacitance. So that's called a varactor. Okay, that's another. Okay, so let's cover then the optoelectronic diodes, because that's probably most commonly encountered today in your lives. Okay, so in an optoelectronic diode, okay, it's just a PN junction diode. And what's shown here, okay, is this under reverse bias or forward bias? Reverse, very good, all right. And we show, this is from the textbook Perret. It clearly shows that we have light shining on this junction. The absorption length, or the depth to which light is absorbed in various materials actually depends on the wavelength. In silicon, within the visible light spectrum, it can be microns of depth. So, you know, you'll have photons reaching the P side, the depletion region, and the N side. So let's just assume that we have lots of light shining on all regions of the PN junction diode, so that electron-hole pairs are generated in all regions. Okay. So now this electron-hole pair that's generated due to light is not going to contribute to current because it's more than one diffusion length, minority carrier diffusion length away from the from the depletion region. Okay, so this is not going to contribute to current, and in this cartoon, this electron hole pair is not going to contribute to current again, because likely these will, once they get generated, they'll move around and eventually recombine before reaching the depletion region. Okay, so that's just illustrating that really it's only the carriers, the electron hole pairs generated within one diffusion length of the depletion region that will survive long enough to reach the depletion region and get swept across. And we're talking about minority carriers being generated here. Okay, so let's assume that there's a certain rate at which the electron hole pairs are being generated. This extra reverse current, okay, notice it's reversed, so it has a minus sign, due to light. So the reverse current due to light shining is going to be proportional to the rate at which you're generating electron hole pairs, and it's going to be proportional to the volume in which you're collecting the generated minority carriers to be swept across the junction. So that's the cross-sectional area times the length, the total length of the diffusion, the diffusion lengths and the width of the depletion region. Yes, Paroma. Yes, so you're right. So we're assuming simplistically that the rate at which, so GL is constant throughout the entire diode, even though in reality maybe the rate of generation will be slightly slower as you go deeper and deeper into the silicon.
And then this is when light is on.
That's true, yeah. So usually you have a PN junction, okay, well it's usually like M plus and then P on the bottom. And you'll shine light, into one surface. Yeah. Okay, so I think. Yeah. Any questions on just this? What's happening on this slide? So basically, I'll call it EHP, electron hole pair. Sorry, only minority carriers generated within one diffusion length. Length of the depletion region are collected and therefore contribute IL. Okay. All right, so just qualitatively, it's shown in more detail on the next slide. If you have IV, this is the normal IV characteristic ideally for a diode on a linear scale. With light, let's draw. Light, you're just going to add, it's going to look exactly the same, except it's going to be shifted down by. So the ideal diode equation still holds. It's just that you add this negative component of current. Okay, so let's zoom in to this region here, sort of near zero, on the next slide. Okay, so an interesting performance parameter for a light optoelectronic diode is the open circuit voltage. Oh, okay, so let's not talk about that first. So if we operate a diode with VA less than 0, this is actually a photodetector, a light detector. So if you put a reverse bias on your diode and have a circuit that detects whether or not current flows, in other words, you can put a resistor in series with the diode, and if a voltage appears across that resistor, that means current is flowing through the diode because the resistor is connected in series. So you can detect a voltage, and it's like, okay, there must be some light shining on the PN junction. Okay, so that's basically fundamentally how a photodetector works, but we'll cover this in a little bit more detail later. Okay, but now we operate with the applied bias greater than 0 for a solar cell. As indicated here, if you operate your solar cell, if you bias it at this point, this corner operating point, that's where you can maximize the current times the voltage, the magnitude of the current times the voltage. So just generically, if you have a circuit element, you have some voltage applied across it and some resulting current, the power is equal to I times V. Okay, but here for a solar cell, the power is I times V, but it's negative if you operate the solar cell in the fourth quadrant. Okay, so if the power is negative, that means this element, the circuit element, is generating power rather than dissipating power. So that's what a solar cell does. It's used to generate power. Okay, so let's draw the open circuit voltage here. So that's defined to be open circuit voltage because that's where the current is 0. Like if you have an open circuit, in principle, no current can flow between the two terminals. So I is 0. So this is the open circuit voltage. And typically, well, it's shown here on this slide, but typically for silicon solar cells, the open circuit is about 0.6 volts. And the other interesting point here is the short circuit current. So this is the short circuit current, I sub SC. So short circuit means, okay, if you have a short between two terminals, there's no voltage drop across them. So this is the current that flows when the voltage is 0. And so ISC typically, okay, it depends on the area, right, the junction area. So I'll just give it to you in terms of amps per centimeter squared. So depending, oh, so this is JSC, sorry, JSC. So depending on the area of the solar cell, you can get this much current to flow. Okay? So all right, so this is the optimal operating point here. Okay, and a lot of times you can hear, let's see, this is something called a fill factor, right? A solar cell fill factor. So that's defined to be the power output over ISC times VOC, right? So imaginary, I mean, if, of course, the curve is not square, but if it were ideal square, then the maximum power that your solar cell can output is just going to be right at the corner here where the ISC, horizontal line and vertical line intersect. Okay? And typical fill factors today are maybe 75%, something like that, for a silicon solar cell. But clearly, hopefully, it's not too hard to see qualitatively. If you operate your solar cell with too high of a voltage, then your current, if you go this way, the current is reducing, so IV product will go down. And if you operate with lower voltage, although the current is higher, the voltage is lower, so the power goes down. So to maximize the IV product, you have to operate pretty much right at the knee of the curve. Okay? And that's kind of a practical challenge for solar cells today, because you usually have many solar cells connected either in parallel or in series, and due to manufacturing variations in the manufacturing process, this optimal curve, this optimal operating point is actually slightly different from one cell to another, and that makes it kind of hard to get the most energy efficiency out of an array of solar cells. Okay, let's look at a solar cell structure in detail. And I forgot to bring a solar cell, but does anybody have a calculator on them, or have you? Yeah. So let's see. Let's look at. Do you have a solar cell on your? Not environmentally conscious. No, I'm just kidding. Does anybody have a calculator with a solar cell on there? You have all TI graphing calculators. TI is very happy about that, I'm sure. Okay. So do you remember kind of what a solar cell on your calculator looks like? It's kind of, first of all, is it shiny? Is it? Oh, you got one. Thanks, Bjorn. So it's pretty dark. If you look at it, if you're willing to pass that around. And it has some shiny parts. It does have some shiny parts. Right? So it kind of looks, if you look at this, a solar cell, it's kind of dark, and then you see these shiny lines going across it. Okay? So those shiny lines are the metallic conductors that electrically conduct current, out of the solar cell. So you do need to have, okay, so it's a stack, NP diode stack. And you have to make contact on one side where light is shining in. And you really don't, so metal, the electrical conductor, first of all, is opaque, so you sort of want to minimize the area so the surface area that is occupied by these metallic conductors, you want to minimize that. That's why they're skinny little lines, right? Because you don't want to have light shining on the solar cell and reflecting back. Okay, because anything that's shiny is actually reflecting light back at you. On the back side, it doesn't matter, so it's usually a complete metal layer at the back side, because light is only shining in on one side. So light shines in, and electron hole pairs are generated. They diffuse and are collected. So majority carriers are collected at the P and N contacts. Okay? So this is a typical representative cross-section of a solar cell structure. Okay, so one side is N-type, other side is P-type, and at the metallic contacts, it's more heavily doped to get ohmic contact. Now the surface is intentionally roughened. Okay, so why is the surface intentionally roughened? Surface area. Oh, okay, that does happen, but that's not the reason why it's done. Less reflection. So that's what's illustrated here. It's not a really nice, photon kind of symbol, but you have light coming in. Some of that light will be diffracted and enter the p-n junction and generate an electron hole pair that can result in negative current. A part of that will be reflected, and if the surface is roughed, then basically that light, that reflected light, has one or more opportunities to enter the silicon again. So if you have a perfectly smooth surface, which is what most integrated circuits start out with, you'll reflect so much of the light that it's not going to be an efficient solar cell. Right? You want to have as much of the light shining into the cell to generate electron-hole pairs to generate electricity. So a relatively small amount then is reflected back, and that's why it looks black. Right? If something looks black, that means very little of the light is reflecting back into your eyes. So the question is, how do we achieve in practice that rough surface? So it turns out that we can do this by actually forming a mask. So it's actually shown here on the right. So what we do is we first form strips of, let's say, silicon dioxide. So it's very easy to oxidize silicon. You heat it up in a oxidizing ambient. You can grow a thin film of silicon dioxide on the surface, and then you can use microfabrication processes to pattern that oxide into, let's say, a grid of stripes like this. Okay, so you have a grid of oxide on the surface of the silicon. Okay, but in between those strips of oxide, you have silicon exposed. So I'm just going to draw a cross section. So you have, let's say, some oxide stripes like this on the surface of the silicon. Okay, so in between these stripes, you actually are exposing the surface of the silicon, and we can soak it in potassium hydroxide, which is a chemical etchant for silicon. So the hydroxide, OH species will actually dissociate in this liquid solution. And then it's the OH ions that can react, form bonds with the silicon, and remove the silicon into the solution. So then you can end up etching away the silicon in these regions. So I'm just going to draw it kind of like this, right? So over time, you remove silicon from the surface, and over time, you can etch deeper and deeper into the silicon. Now, it doesn't happen like this specifically, because particularly for this etch, you end up with sloped sidewalls. Okay, so if you etch in potassium hydroxide, it turns out that certain planes of silicon etch more slowly than other planes of silicon. Okay, so specifically, the 111 planes etch much more slowly. It's like more than 100 times. Etch much more slowly than the 100 and 110 planes. So this is due to something. What do you think it's due to? Density. Yes. Surface energy. Oh my goodness. Okay. Yeah. So yes, it's true. The 111 plane does have a higher atomic density. You know, more closely packed atoms than, let's say, a 100 plane. That's true. But a 110 plane, if you remember from homework 1, is actually even denser. It has a denser has a higher atomic density. Okay. So what was the other potential explanation? Atomic density. Okay. Something else. Okay, let's see. Let me try to explain. So it turns out that for a chemical reaction to occur, you need to break the bonds, right? To remove a silicon atom, you need to break the bonds that it forms with its nearest neighbors, right? Okay, at the surface, okay, there's going to be a dangling bond, but there's still bonds holding the silicon in place at the surface to its neighbors, like beneath the surface. Okay, so it turns out that it has something to do with the number of bonds available for reaction. So a 111 plane has the fewest number of bonds available, sort of sticking out, available for reaction with the OH. Dangling bonds, so the question is dangling bonds. It's partly dangling bonds, but it turns out that a silicon atom has to react with 2 OH ions to be pulled out, to be removed from the surface. So I wanted to show you, okay. Do you remember? Okay, so let's look, for example, at a 110 direction. Maybe it's hard to show. But okay, see these bonds over here? They're lined up along a 110 direction. Hopefully you can imagine that. Okay, so if this was the surface, like let's say all the atoms on this side over here are removed, and you have a plane of silicon atoms here, a 110 surface. So clearly there will be a couple of dangling bonds, but the rest of the bonds that are holding the silicon in place are to the side. Okay. Now if we look at a 111 direction, let me find, okay, so this atom right here, okay, it actually does have some bonds sticking out of the plane, but it has, okay, let's look at this atom back here, and let's say this atom here was removed. Okay, so now this atom back here will have one dangling bond, but it will have three dangling bonds, three covalent bonds holding it in place in the silicon. So that's kind of what I want to show you. All right, so I got, these are actually LEDs inside here, so that's to prove another point later. But basically for silicon at the surface, if you have, let's say if you're an OH atom, no ion, and you want to grab my bonds, is it easier if they're like this or like this? Right, sticking behind me, right? Like this. So that's why for 111, the bonds that are holding the silicon atoms in place are kind of aimed backwards. So it's harder to form a reaction, to grab the bond, to break the bonds, form a reaction to get the silicon away. Was there a question here? Okay. So that's the fundamental reason. It's not actually atomic density. Atomic density has something partly to do with it, but it's really the bond configuration, physically the bond angles in the 111 plane versus in the 100 and 110 planes. Okay? Okay, so to finish this sentence, so it's due to a lower density of dangling bonds for reaction with OH. Okay, so like if the bonds are kind of sideways, it's easier to break them to have a reaction with OH. Okay. All right. So then, if you etch with time, over time, then you end up with. Oh, okay. So then the key here is that each of these sidewall surfaces is a 111 surface, right? Because those are etching more slowly. The silicon is etching faster, like vertically, in the 100 direction. So on this slide here, I should have pointed out that this plane, this direction sticking out, is a 111, I guess, 111 direction. Okay, any questions? Oh, okay, I'll ask a really quick question. So you might have heard of stacked solar cells. Okay, so light is absorbed by electron-hole pair generation, but the visible spectrum of light, or the solar spectrum, has many, many wavelengths, right? There's a whole range of wavelengths. So there's a whole range of photons that the sun gives off. So it turns out that you can improve the efficiency of a solar cell if you actually have layers of different band gap materials. So you have, let's say, a small band gap material to generate more efficiently electricity from the low energy photons, so longer wavelength, and you have a wider band gap material to generate light from higher energy photons, shorter wavelength light. So my question is a general question: if you were to stack solar cells, like layer 1 and then layer 2, layer 3, these all have different band gaps, and here's the direction of light shining in. which material, which solar cell would you actually shine light on first? That means up here versus down here. Largest band gap first, that's correct. So what happens if you shine light on a semiconductor and the photon energy is much, much greater than the band gap energy? The electron will go up like, okay, I'm just out of here. It'll go up with, I mean, the energy is going to be equal to the photon energy. So the electron will be generated with a lot more kinetic energy. And that energy, due to collisions, is going to be lost to the lattice. So you're going to heat up, you're going to waste that energy due to heating of the cell. So you basically want to absorb the higher energy photons first with the larger band gap solar cell up here. So you want large EG up there and the smaller EG down here, right? So you can actually efficiently absorb the photon energy across different regions of the visible spectrum. Yes, question? Okay. The question is, why is the current collected through the backside this way? You mean like only locally? That's a good question. I'm not quite sure. I can find out though. But does anybody have any guesses as to why you would only form the ohmic contacts locally? I'm not sure if it has to do with maximizing efficiency as well, but I'll check and find out, and I'll let you know next time, or I'll post it on the Piazza website. So I guess the question is, why would you only form ohmic contacts in certain regions on the backside? Because in principle, you could form this whole backside as P+, right? Oh yeah, that's a good point. So typically, so let's say light shines through, and these solar cells, depending if it's single crystalline silicon, then it can be hundreds of microns thick. If it's glass, thin film, then it might be only microns thick. But yeah, so that's a good reason that basically there might be some light that hasn't generated electron hole pairs yet, and you don't want it to escape the backside. You want it to reflect back in and have another chance of generating electron hole pairs. So that kind of would make sense. Okay, so the question is, are the heavily doped regions more opaque? I mean, they have smaller band gap due to band gap narrowing, but they shouldn't be, I mean, and so due to that, I suppose you could say it's more opaque, but it's not going to be significant. But certainly, yeah, a smooth metallic backside here could help to reflect the light back into the semiconductor region. But I'll verify that. Good. Yes, question? How does the light come to the bottom? Okay, so there are a lot of photons. Not every one of them will be interacting with an electron hole pair, near the surface. So basically, there's this typical characteristic length. So it's called the absorption length, where so it's typically, depending on the wavelength of light, it can take more than a micron for a photon to, on the average, to create an electron hole pair. So there's always going to be, so it'll be an exponentially decaying function. So the intensity of light is going to be an exponentially decaying function with distance, but that characteristic length over which it decays depends quite strongly on the wavelength of the light. So I think we had. We can look at let's look at the absorption spectrum. Coefficient. Okay, let's look at coefficient. So, okay, this is, okay, so absorption coefficient, okay, so that's alpha, okay, and you can see it's, and this is in centimeters, so it's strongly dependent on the wavelength of light. And the wavelength of visible light, okay, the solar spectrum is from about 0.3 to out here, like a little bit more than a micron. So you can see it varies over orders of magnitude. Okay, so 10 to the 4, so this is 1 micron right here. So this is like kind of green light. For green light, it's on the order of a micron. Well, 1 over a micron. Okay, so the absorption coefficient, let me go back here. Okay, so the intensity of light going into, okay, so this is I, sorry, this intensity of light, okay, it's not current. I is proportional to e to the minus alpha x, where x is this distance here, right? So that's the absorption coefficient. And as I mentioned, so it depends on the wavelength of light, can vary over orders of magnitude. So that's how some wavelengths of light, like the longer wavelengths of light, can travel deeper in silicon. Okay, PIN photodiodes. So you'll have a homework problem on this. So remember again, we're operating the diode in this regime. So with light, well, I guess I should just shift it. So with light shining on this PN junction, you can detect a change in the reverse bias current. Okay. Now normally, as we talked about earlier, you have to wait for so most of that current is due to carriers generated in the quasi-neutral regions. So you have to wait for the carriers to diffuse into the depletion region to be swept across the junction, and then once they become a majority carriers, then current can flow out of the PN junction diode, right? So you have PN. Okay, so you generate carriers, okay, like holes over here, and they diffuse toward the depletion region, get swept across, and then they end up flowing out this contact. Minority carrier electrons generated on this side have to flow all the way across here before you can detect it in your circuit. So it takes a long time, or some significant time, for the carriers to diffuse to the depletion region and then get swept across at the drift velocity. So sometimes you would like to have a really fast response time, like 10 gigahertz operation speed. So you really don't want to have to wait for carriers to diffuse to the depletion region before you can detect them. So one way to deal with this is to actually fabricate a PN junction diode with this intrinsic, very, very lightly doped region between the P and the N regions. And what happens then is that, okay, you have a PN junction. So between the P and N contacts, you still have the same total difference in work function between each side of the junction, right? So the built-in potential is exactly the same with or without that intrinsic region, right? Because the built-in potential is just going to be dictated by the difference in work functions at each end of the diode. So the built-in potential is the same, but the depletion region is going to be enhanced by that intrinsic region. So basically, this means that you're dropping the same voltage over a longer distance. So the electric field is going to be lower, but the region where you have an electric field is going to be larger. So in other words, there will be so you can actually have microns, or many microns thick intrinsic layer. And so you can actually make the intrinsic region contribute more to IL, the light generated current, than the diffusion current. Okay, so this is a simple, so the energy band diagram, you have very little voltage dropped in the P and the N regions. Most of the voltage is going to be dropped across this depletion region, the intrinsic depletion region. And so if you make that intrinsic layer really thick, you can generate a significant amount of current with light shining on it. And immediately, once electron hole pairs are generated, they get swept out. So that's why you can have faster response time. Okay? So this is in contrast to in the quasi-neutral regions. as in a PN diode. All right, and if you want, you can operate or bias this, reverse bias this diode near breakdown, so like around here, so that once you generate electron hole pairs, you have some chance of avalanching to occur, and the avalanching can increase the current that's generated in the depletion region. So you can actually have very fast and very strong current signal when light shines on your diode. Okay? All right, and then finally, light-emitting diodes. So I already passed around a light-emitting diode for you to take a look at. It's just a little chip, if you remember, and you can turn it down so you can actually see the little chip and see light coming out from that chip. So as alluded to earlier, light-emitting diodes are made with 3-5 compound semiconductors, which have a direct band gap. And depending on the energy band gap, the wavelength of the light that's emitted, this is a nice handy formula, 1.24 microns over the band gap energy in EV. Okay, so the band gap of silicon is 1.12, so if you take 1.24 divided by 1.12, it's a little bit over 1 micron wavelength of light that's emitted by silicon LED. So that's not within the visible spectrum. So let's review, what is a visible spectrum? How about, does anybody want to say what red is? It's like meters. Green is, I think these numbers are not too hard to remember. I'm not going to expect you to remember this for the exams. But just to let you know, it's on the order of, it's certainly sub-micron. It's anywhere in about half a micron wavelength. And here's a little picture of a LED. So you have light coming out actually in all directions, and this is a reflecting holder that's used also potentially to bias one side of the PN junction. And light comes out and is reflected, and this package is shaped to help aim the light out at the viewer. Okay, so here we have light, or a photon is emitted upon recombination. Okay, and where does the recombination occur? Primarily quasi-neutral regions. Very good. Okay, so why are light-emitting diodes so becoming more and more common? So what are some of the advantages of light-emitting diodes over, let's say, a fluorescent light bulb or incandescent light bulb, which you probably don't see it anymore? It's been banned, I guess. What are the advantages of LEDs? Yes, so some good things are energy efficiency, but this is compared to an incandescent light bulb. So it can be approaching maybe 90 lumens per watt. So that's actually comparable to a fluorescent light bulb. Okay. What else? Yes. Yeah. So compact size, and the voltage required, yes, is lower. Okay. So that's actually going to be a homework problem. But typically, what kind of voltage do you think is going to be needed to forward bias this light-emitting diode, just roughly? 2 volts, 1 volt. Yeah, it's on the order of 2 or 3 volts. So depending on the band gap, right? Depending on the band gap energy. So remember, the built-in potential for a PN junction diode it's comparable. It's less than, but it's comparable to the band gap energy. So you need to overcome that. You have to reduce that potential barrier to let significant current flow. So the larger the band gap, the more voltage you need to apply to allow significant current to flow, to have significant light coming out. Okay. So yes, compact is a great advantage because, like for example, these things have light-emitting diodes in them, so you can see them at night. But you can see in cars, they have more and more of them using LEDs instead of light bulbs to light them up in the pretty fancy designs. There's one more advantage of light-emitting diodes. Cost is actually not one of them. Cost is a disadvantage compared to, let's say, a conventional light bulb. So cost is, in terms of area of illumination, the chip size, so a typical LED will be a few tens of cents, like 20 cents, 30 cents, depending on the color. So compared to a light bulb, in terms of area that it can illuminate, it's more expensive. Okay. Doesn't fit? Yeah, that's right, lifetime. Okay, so a lifetime, does anybody know typically how long a LED will last? Yeah, right, so it can approach 100,000 hours. And so cost, just initial cost is higher, but over a lifetime, you don't have to replace it as often. So let's say in traffic signals, light signals, you don't have to replace it as much. So it turns out overall, it is actually lower cost for a lot of these applications because you just don't need to change them out as often. So a lot of advantages to light-emitting diodes, and a lot of research being done to lower the cost so that we can use them, let's say, even for room lighting. So over large areas, we can have some cost-efficient light sources. Yes, Ross? What is the failure mechanism? Oh my goodness. Okay, let me look that up and I'll get back to you next time. Okay, so I'll get back to you on two things from this lecture. Okay, we'll find out. Okay, so the social hour today, I think it's Mediterranean food. And Professor von Meyer, who you can ask her to explain the power outage that we had on campus. Her area of specialty is power systems.